a new graph theoretic notion, P4-free partition and cover numbers that we introduced in a recent work. This is a joint work with Simina, another of our colleagues at the computer science department, and two of my grad students, Himanshi and Tamalika. So, sorry, okay. Today we will be considering bipartite graphs particularly, and we will introduce two new graph theoretic concepts called P4-free partition and cover numbers. And there will be several applications of these two concepts to various fields like information theory, cryptographic complexity, measuring cryptographic resilience, communication complexity, and combinatorial optimization. And all these connections are established by modeling joint probability distributions and Boolean functions as bipartite graphs. At the end of the talk, we will discuss several open research directions, and all the help that you can provide is welcome. So here is a quick outline of the talk. First, we'll go through the application scenarios. So you can choose your favorite application scenario and follow the talk along with that particular example in mind. Then we will define what P4-free bipartite graphs are and how they relate to the applications that we discuss. Next, we'll introduce the P4-free partition number and cover number, and we'll go over their applications and results that we have. And finally, to conclude the talk, we'll have several open research directions. So let me introduce the first example. So if you are from information theory, this example is should be particularly meaningful to you. So we have a joint distribution, X and Y. The sample X is given to Alice and sample Y is given to Bob. There is a deterministic Genie who gets access to both the samples X and Y and provides some suggestion or assistance Z to both Alice and Bob. And the objective of providing this assistance is the following. Alice and Bob want to agree on a secret key. And whatever randomness that remains in their sample, for example, Alice's sample is X, and she has already extracted the shared key S, then the sample X conditioned on S should be her local randomness, RA, and similarly, Bob will output his leftover randomness, RB. The objective here is that RA and RB are independent of each other. Okay? So the question that we are going to ask is, what is the minimum assistance that is needed from a Genie to achieve this objective? At this point, we can pause, and if there are any questions, please feel free to ask. I can wait for a couple of seconds at this point. So as a comment, I want to mention that similar problems have been considered, for example, in Wiener's common information, where you insist that the random variable S is the empty set. You do not want them to establish a secret key. Okay, so let's move ahead and see how this application could be useful. So we consider a variant where Alice and Bob get the samples, but there is no Genie anymore. But however, Alice and Bob participate in a communication protocol. And we can ask, what is the minimum communication needed so that Alice and Bob can extract the shared key S and individual independent private randomness, RA and RB respectively. One quick observation here is that the entire communication protocol can be simulated by the Genie. For example, the Genie knows X, so it can simulate the first message of Alice in this communication protocol. Once it simulates the first message, it knows Y, so it can simulate Bob's reply, and so on. So the lower bound in this setting is at least the lower bound established in the previous slide. So this is one way of utilizing such lower bound results. In fact, we can do something more. Suppose Alice and Bob have access to secure computation boxes. So these FIs can help you compute message forwarding functions, oblivious transfer, NAND gate, any other form of Boolean gates, for example. And again, the entire transcript can be simulated by the Genie. So the minimum interaction needed to achieve this objective of agreeing on shared key and obtaining independent private randomness is lower bounded by the original application scenario that we saw. So these are the applications to cryptographic complexity of the original problem that we studied. Sorry. The next example is a cryptographic resilience problem. So a famous problem in cryptography is that you are given two samples, X and Y, from a joint distribution. And Alice and Bob participate in a communication protocol. At the end of the protocol, Alice outputs two random bits, R0, R1, and Bob outputs a bit, random bit B, and the random bit R subscript B. So this computation is referred to as general secure computation. The problem with this setup is that X and Y needs to be stored with Alice and Bob for a long period of time, and therefore it is susceptible to leakage attacks. What can happen is Bob can obtain lambda bits of leakage from Alice's sample X, and then this protocol need not be secure anymore. So the question that arises here is how much bits of leakage does Bob or Alice need to rule out the possibility of general secure computation? We will see that this also can be solved using the problems that we introduce in this talk. The third application, and somewhat different, is computation of a Boolean function, f, relative to a equality oracle. Okay, I will explain this further. We'll explain this further in this talk, in this slide. So Alice has input X and Bob has input Y. I want to emphasize that there is no a priori distribution on X and Y. I'm saying arbitrary X and arbitrary Y in the domain of F. They receive non-deterministic input Z, and Alice, using X and Z, computes X prime, and Bob, using Y and Z, computes Y prime. And X prime and Y prime are fed into the equality oracle, and the output of the equality oracle is the output of this communication protocol. So there are two constraints that one needs to satisfy. If f of x comma y is 1, then there exists a non-deterministic input such that the output is 1. Okay, I want to emphasize that it says that there exists one, there may be more than one. Okay, this is slightly different in flavor from the previous two applications that we saw. So here, the non-deterministic input, there might be multiple non-deterministic inputs that lead to an accepting path. On the other hand, if f of x comma y is 0, then there are no non-deterministic inputs that can lead to acceptance or the output being 1. So why do we consider this system? One needs to understand that computing equality without equality oracle is very expensive. So we want to study what additional power does one call to the equality oracle provide us. So therefore, we are trying to understand the relative complexity of computing a function f with respect to one call to the equality oracle. The communication complexity of such a protocol is the support of the non-deterministic input Z, the various values that it can take. The total size of that set is the non-deterministic communication complexity. The question here now that arises is, what is the minimum or the smallest non-deterministic input Z that suffices to compute a function f? And this will be a slightly different this problem will be slightly different than the first two applications that we saw. Okay. The fourth application is characterizing speedup due to parallelism in combinatorial optimization problems. So I have chosen a particular optimization problem here, and I think if each one of us can think of an interesting optimization problem that can be cast in this template. So my favorite problem coming from crypto is that there is some data and there are some users. So the rows in this matrix are users, columns are data, and the shaded entry represents whether a particular user has access to a particular data or not. So one strategy is to multicast use multicast. So let's consider this strategy. What it says is that these data are being multicast to these users. So a rectangle represents the fact that a set of data is being multicast to a set of users who had access to it. And the first strategy says that we can use one multicast, second multicast, and a third multicast to enable each user access to the data it wants to look at. Okay. However, one needs to observe that these two multicasts, the first and the last multicast, could be parallelized. So in fact, you do not need 3 time units of time. You could use the parallelism to collapse or have 2 multicasts in parallel. So these set of data will be multicast to these users, and these set of data can be multicast to these users because each of these multicasts have separate users and separate data. Okay, so the speed up achieved due to parallelism is something that we'll quantify in this talk. Any questions about these applications? Then we can move to the formal definition part. Okay. So first, let me define what is a P4. P4 is a path of length 3 over 4 vertices. Okay. And in particular, since we are restricting our discussions to bipartite graphs, we have left partite set and a right partite set. And a path of length 3 looks like this. A P4-free bipartite graph is a graph in which, if you look at the induced subgraph by any 4 vertices, you do not have a P4. So it can either have 0 edges, 1 edge, 2 edge, or 4 edge, but it doesn't have 3 edges. Okay, that's the important part. So we will be considering bipartite graphs that are P4-free. So what it actually means, it means that a P4-free graph is actually a graph in which each connected component is a biclick. And this class of graph has been very widely studied in mathematics since the 70s under various different names. I have chosen the name P4-free just because it's descriptive of the property rather than the other names that are written here who describe how the graph was generated. There's a difference between these two stories. So that's why we have gone for the name P4-free. So let us gain some intuition about this using some pictures. So first, let me provide intuition about what a biclick is. So we have 2 partite sets, L and R. there is a subset of L called L prime and a subset of R called R prime. And a biclic is a bipartite graph that includes every edge between L prime and R prime. Okay. So if you look at the right, we can represent the adjacency matrix of this graph as follows. Rows are vertices of L and columns are vertices in R. L prime is a subset of rows and R prime is a subset of columns. So if every edge between L prime and R prime is included, then what we get is a rectangle. So what I want you to imagine henceforth, pictorially, every biclic is equivalent to a rectangle. So in special cases, if you have only one edge in a graph, that is also a rectangle. It's a rectangle of dimension 1. Stars, the center is on one partite set and leaves are in another partite set. That is also a biclic, special case of biclic. Now, P4-free bipartite graphs are graphs such that each connected component is a biclic. So here, I want to emphasize that the connected components need not have same size. So for example, the first connected component here has equal left subset and right subsets here, vertices, while the second and the third do not. So pictorially, a P4-free bipartite graph is something like this. It looks like a disjoint union of rectangles. Okay? This is the formal definition of a P4-free graph. And now let's look at some special cases. Matchings are P4-free bipartite graphs because every connected component is an edge and edge is a biclic. So a matching is a P4-free bipartite graph. Star forests, every connected component is a star, is also a P4-free. A biclic itself is a P4-free bipartite graph because it has one component and it is a biclic. Okay? Any questions at this point?
So Maji, a quick question.
Yes.
For me, this definition looked like a theorem, but this is a definition actually, yes? Because I saw your P4 definition was if there is no P4 in the bipartite graph.
Yes.
But right now, it's like a characterization for me.
Yes, it's a equivalent characterization. And you can obtain this by doing a breadth first search from a node.
Okay.
It's a very simple proof if you do that. It gives this characterization. Yes, you are absolutely correct. It's an alternate equivalent characterization. So yes, I want to say that we want to carry over this image of a P4-free graph being a disjoint union of rectangles. Okay, so I need to now explain how we are going to encode joint distributions as bipartite graphs. Suppose we have omega A, samples of Alice, and omega B, the sample space for Bob's samples. A flat distribution is a uniform distribution over this subset of omega A cross omega B. Okay, let's take an example to understand what is a flat distribution. So the distribution that we are going to consider is forward or flip all distribution represented by FFN. So the sample spaces of Alice and Bob samples are n-bit strings. Alice receives a uniform and independent bits B1, B2, Bn. Conditioned on Alice sample, Bob either receives identical bits with probability half or every bit is flipped with probability half. Okay, so all joint samples are equally likely. That's why this distribution is a flat distribution. Okay, let's consider how we can represent a flat distribution as a bipartite graph. It's just very natural. The idea is Alice's sample will be vertices on representing rows. Bob's samples will represent columns. And a intersection of a row and column is 1 if and only if that joint sample is possible. Otherwise, it is 0. Let's take this example. Suppose n is 2. In this case, if Alice receives 2 bits 0, 0, then Bob can either receive 0, 0 or 1, 1. But it cannot receive 0, 1 or 1, 0 because the bits will be either directly all communicated or every one of them will be flipped. Similarly, we can construct this entire matrix, and this matrix represents a bipartite graph. Interestingly, we can rearrange this matrix by permuting the columns and the rows such that we have a block of rectangles, a block of ones and a separate block of ones. So this is a rectangle and this is a rectangle. So what I want to communicate here is that the graph corresponding to this distribution is a P4-free graph. So here is a characterization that we provide in our paper. Suppose there is a joint distribution XY and it needs no Genie's assistance. Then it is equivalent to the fact that the graph corresponding to X and Y is P4-free. Let's take this example of forward of flip all for n equal to 2. In this case, there are 2 connected components, the first one and the second one. So the secret key is the identity of the connected component. You can take a look that x1, xor, x2 for all these entries are identical to 0, and everyone here is 1. And this is something that Alice can obtain by x1, xor, x2, and Bob can also obtain by y1, xor, y2. The local private randomness is x1, the first bit of Alice, and private bit of Bob is independent randomness is y1. You can convince yourself that y1 and x1 are independent of each other. The idea is because it doesn't depend whether x1 is 0 or 1, Bob's distributions are identical. So this is why we are studying P4-free graphs, because these are the graphs that need no Genie's assistance in our first application. Actually, it's just not something particular to forward or flip all. It holds for any P4-free graph. So the secret key is the identity of the connected component. Once we conditioned on the connected component, then X conditioned on this identity and Y conditioned on this identity of this connected component are independent of each other. Because it doesn't depend what row you are looking at, the conditional distribution Y condition on S is identical. So they are uniform and independent. This is another result. This is our second application to measuring cryptographic resilience. If X and Y is a P4-free graph, it was proven in 2000 by Joe Killian that you do not need to perform any leakage. Every secure computation protocol will be broken. So it has 0 resilience. The third application, okay, if a function, if the function looks like this, what I mean by that, the ones form the rectangles and zeros are the white areas, then it is very easy to compute this function without any assistance or without any non-deterministic input. Alice can compute the identity of the connected component X prime, and Bob can also compute the connected, the identity of the connected component Y prime. And the output of the function is 1 if and only if X prime is equal to Y prime. So again, this is how P4-free graphs show up for in communication complexity problems. For Speedup, let's take this example. Suppose there are 3 multicast sessions, the red session, green session, and the blue session. They can be parallelized if and only if each of these multicasts, the columns are mutually disjoint, and the rows corresponding to each of these rectangles are also mutually disjoint. This is equivalent to the definition of P4-free, and therefore they can be parallelized. Okay, so this is the motivation of why we are studying P4-free graphs. So now let me introduce the first concept that we introduced, P4-free partition number. Okay, suppose we are given a graph G. Our objective is to find minimum number of P4-free graphs, GIs, such that their edge sets, E1, E2, En, partition the original edge set of the graph G. Okay, so every edge in G is associated with one of the graphs, edge sets of the graph's GIs. It's a partition of the edge. I am emphasizing this repeatedly because vertex partitioning is a completely separate concept and has been studied earlier. The edge partition has not been prior to our work. I want you to observe that if the graph G itself is P4-free, then its partition number is 1, because you need only one graph to cover all, account for all the edges. So for example, forward or flip all distribution has partition number 1. Any questions about this definition? Okay, so let me move ahead and introduce another example. So consider the noisy typewriter distribution. Okay, again, Alice samples are n-bit strings and Bob samples are n-bit strings. The probability distribution is as follows. Alice receives a random number whose binary representation is the n-bit string. Bob receives either the same number or one more than the number. Okay, let's take this example and try to understand this. Suppose Alice receives 0, 0, that is 0. Then Bob either receives 0 or 1. If Alice receives 1, then Bob receives 1 or 2. If Alice receives 2, then Bob receives 2 or 3. If Alice receives 3, Bob receives 3, or 4 mod 4 is 0, so 0. I want you to take a look at this graph, graph represented by this matrix. This is actually a cycle. This graph is a cycle of length 8, in general 2 to the power n plus 1. Okay. So observe that this graph is not a rectangle and there is only one connected component. So obviously it is not a P4-free graph. However, we can take this graph and edge partition it into 2 pieces, 2 graphs, such that each of them is disjoint union of rectangles. Okay, so we can claim that its partition number of noisy typewriter is 2. Any questions at this point? So recall, forward or flip all had partition number 1 because it itself is P4-free, and noisy typewriter has partition number 2. So now let's establish the connection between P4-free partition number of a graph and the original information theoretic problem that we posed. Suppose XY is a flat joint distribution. G is the bipartite graph corresponding to this joint distribution, and Z with Genie's assistance. So we can prove this. In our paper, we prove this, that the support of Genie's assistance is at least as large as the partition number of G. And furthermore, equality is achieved. there exists a Genie strategy such that Alice and Bob can agree on a shared key and obtain independent randomness using that optimal Z. And the support of that optimal Z will be exactly the partition number of the graph G. So the intuition is very simple, that if you fix a suggestion of the Genie, then no additional communication is needed for Alice and Bob to achieve their objective. So conditioned on that Genie suggestion, the graph must be P4-free. And since the Genie is deterministic, every edge generates a fixed Z. So the edges are partitioned into these graphs. So that's why the partition number is relevant in this context. Any questions? Okay, now I need to make a case why we needed to introduce something new. Why don't existing concepts take care of this quantity? So for example, something like Shannon's mutual information is identical for forward of flip-all and noisy typewriter, but they are completely different partition numbers. So obviously, mutual information is not the correct quantity to look at. If you consider Weiner's common information, it rules out the possibility of generating any secret key. It is a significant overestimation of how much assistance is needed. Okay, but this Weiner's common information is closest in essence to what we have proposed in this paper. Gach's corner common information, I feel, is too pessimistic. It basically says that Alice and Bob, without computing what is the longest key that they can agree on. I want to emphasize that Alice and Bob can never agree on a key if they start with noisy typewriter correlation. So it's too pessimistic. And any non-interactive object like non-interactive correlation distillation, non-interactive simulation of joint distribution, or any of these quantities are too pessimistic. So we need some assisted common information, particular to the applications that I motivated initially. There are edge covering measures that are similar to what we have proposed, but however, all of these are significantly imprecise. I want to bring to notice the first quantity that we are looking at, bi-click partition number. This partition number, this is the minimum number of rectangles needed to partition the edges of a bipartite graph. And this is actually closely related to what Weiner's common information is. And that's why I said in our object is closest in essence to Weiner's common information. Bi-click cover number, on the other hand, is significantly well studied. However, it is completely unrelated to what we are studying. Okay, any questions at this point? Otherwise, we'll move to results now. Okay, so let's try to understand how large can P4-free partition number be. The idea is the following, like something like a matching, which is very sparse, has a low P4-free partition number, 1. Something very dense, like a complete bipartite graph, is also partition number 1. So what is the actual characteristic that determines high partition number? Okay. Let me go ahead and say this. We do not have a good characterization for that, but we will still show you how to construct graphs with large P4-free partition numbers. Suppose the partite sets are of size n. I want just a technical comment here. This n is capital N. And the way you should think of this n is it is 2 to the power little n in our context. All previous indices had little n in them. Here, henceforth, we will be using capital N because the total number of vertices was exponential in the parameter little n. So first of all, we know that it cannot be too large. There is a highly non-trivial result by Al Gore and Alon, who show that the star arboricity of a graph is at most n by 2. Since a star forest is also a P4-free graph, So star arboricity is an upper bound to the partition number of a graph. So we know that it cannot be more than n by 2. I will prove to you in the next slide that we can construct graphs whose partition number is n to the power 1 minus 2 epsilon and multiplied by epsilon, where epsilon is 1 by 3, 1 by 4, or 1 by 5, and so on. If you put epsilon equal to 1 by log n, you get this interesting result that if you consider hereditary graphs, random graphs where every edge in the biclic is independently chosen with probability half, then its partition number is at least n divided by log n. It's quite high. However, all these numbers are sublinear, and the upper bound that we have is linear. So there is still a gap in these quantities. Any questions? Okay, then we go and prove this result, okay? So here is the objective of our construction. We want to construct a dense bipartite graph, G, such that it has a lot of edges. However, any P4-free subgraph is very sparse, okay? So let's consider a P4-free subgraph in our graph G. Suppose our graph was K T plus 1, T plus 1 free. What I mean by this is that there is no biclic in G such that its left partite set is of size T plus 1 and right partite set is of size T plus 1. Okay, so this structure does not occur in our graph. Then I can conclude that the width of every rectangle is at most T. Why? First, let me define what width is. Width is the smaller of the two dimensions of a rectangle. Okay, so the red length of the red edges is the width of the rectangle. If there is a rectangle with width more than T plus 1 or greater than equal to T plus 1, then its length is also T plus 1. So there will be a T plus 1 square. That is, there will be a K T plus 1 subgraph. And we had already assumed that G doesn't have any such subgraphs. So the width is upper bounded by T. The cumulative length of these rectangles is the length of the dotted line, which is at most the size of the sum of the two partite sets, which is at most 2n. Therefore, the total number of edges in any P4-free subgraph is at most 2 times n times T. Okay, think of T as a constant natural number. Okay, how do we construct dense bipartite graphs that avoid KT plus 1, KT plus 1? Actually, I don't. We use a probabilistic argument and show that using first moment techniques, there are graphs which have a lot of edges. N to the power 2 minus 2 divided by T plus 2. In previous slide, we saw that every P4-free subgraph has at most 2 NT edges. So you need the ratio of these two quantities, at least that many P4-free subgraphs to account for all the edges in G. That gives this bound. And if you substitute 1 by T plus 2 as epsilon, this is the bound that I had promised earlier. For hereditary graphs, they have n square by 2 edges, and they are K log n free. And that's why you can substitute T equal to log n and get the same result. Okay, any questions? This is the first part of our results that are complete. Now we'll move to P4-free covers. Any questions? Okay. So P4-free cover is the minimum number n such that there are n P4-free graphs G1, G2, Gn such that every edge in the original graph is covered in one of these sets. Okay. So in partition, every edge in G belongs to exactly one P4-free graph. Here it may occur in more than one. Okay, so this is the difference between partitioning and covering. However, every partition is a cover. So we can conclude that the cover number of a graph is at most the partition number of the graph. Okay. A good question at this point is, what is the gap between these two numbers? And the answer is, we do not know. Okay, so this will be an open problem. So if we look at the non-deterministic communication complexity relative to the EQ oracle problem, remember I highlighted in that problem that there might be more than one non-deterministic input that can lead to an accepting path. So that's why this problem is not a partition problem, but a cover problem. And what we can prove is that the size of the support of the non-deterministic input has to be at least as large as the covering number for the graph corresponding to the function f. I'm not going to go into the detail of this, but any questions at this point, I can answer that. Okay, so let me just quickly say that any bound that I proved for partitions, I never use the property that edges belong to only one graph. So actually we proved a stronger bound. We proved that the graphs that we constructed, their cover numbers are more than epsilon n to the power 1 minus 2 epsilon. And for addition graphs, the cover number is at least n by log n, asymptotically, almost surely. Okay. So can we get something better than the arboricity bound? This is an open problem. However, I have a conjecture that I can state here. We can show that in addition graphs, where every edge is included uniformly and independently with probability half, there is a P4-free subgraph with at least n square root log n edges. Remember, this leads to the following conjecture, and I think this is true, that it is at most n by square root log n. And I want to emphasize that we have proven that the cover number is at least n by log n. So the difference is n by log n and n by square root log n. Okay. So let me introduce some useful functions that are studied in communication complexity, and I will show how we can upper bound the cover numbers for these functions. So disjoint n is a function that takes two inputs x and y. X and y are subsets of 1, 2, 3, 4 up till n, this set. So x, you can interpret it as an indicator variable. If you interpret it as an indicator variable, then it is equivalent to an n-bit string. 0 at the ith coordinate indicates whether I is in x or not. Similarly, you can interpret y as a bit string of length n. And disjoint x and y is 1 if and only if x and y are disjoint. Otherwise, the function is 0. Intersection is just the complement of disjoint. And another function that we want to study is the inequality function. So remember, equality is easy to compute given the equality oracle. You don't need any suggestions for it. No non-deterministic input for it. However, for inequality, we want to understand it's the complement of equality. And we want to understand how much non-deterministic input will be needed to compute inequality given one call to the equality oracle. Okay, so inequality is 1 if and only if the numbers are different. Otherwise, it is 0. So the first result I want to present is that the cover number of inequality is at most log n. And the proof idea, I will present the outline of the proof. First, let's take inequality when n is 4. This function has 4 rows and 4 columns. The diagonal is all zeros. Everywhere else, we have ones. Okay, so there is a big P4-free graph here. This set of ones and these set of ones. Let's take that out. Now, what is left over is a recursive structure of inequality of half the size. And therefore, we get the bound log n. Any questions about this? It's a very straightforward proof. So this is really interesting that you can compute inequality by making only log number of equality, logarithmic non-deterministic input. Now I will give a bound for disjointness. So first let's consider disjoint subscript 1. So there is one element. The first row represents empty set for Alice. Second row represents Alice has the element. The first column represents empty set of Bob, and the second column represents Bob has the element. So if Alice and Bob both have the element, then the sets are not disjoint. So it is 0 here. Everywhere else, the sets are disjoint. So we get 1. We can prove, and it's a well-known characterization, that disjoint n is a tensor product of disjoint 1 n times with itself. So I will give a quick proof of this fact as well. So let's take disjoint n when n is 2. So first of all, look at the bottom 2 rows and bottom rightmost 2 columns. All these subsets include the first entry. So they are not disjoint. Okay. Therefore, definitely this part, lowermost, rightmost part, or let's say quadrant, has to be all zeros. This part is a problem of smaller size, where the elements are 2, 3, 4 up till n. So it's a disjoint over sets of size n-1 elements. You can also convince yourself that the other 2 parts are also identical copies of disjoint n-1. If you look at this, this is a tensor product of disjoint 1 with disjoint n-1. And that gives this result. We prove the following fact, that the partition number of a tensor product of 2 graphs, G and H, is at most the product of the partition number of G and the partition number of H. I'm not going to prove this fact. This fact is not that difficult to prove, but we are going to use this to prove the other results. So now we shall use the fact that disjointness has this tensor product structure to prove that it is the cover is at most 2 to the power n/2. So let me give an example. So first I will prove that disjoint 2 has partition number 2. So this is the graph for disjoint 2. I can partition it into 2 rectangles and a matching. And this is the partition with disjoint 2. And disjoint n is just a tensor of disjoint 2 n/2 times. And by using this bound, we directly get this bound. Any questions about this? If the question is how tight is this bound, answer is we do not know. So that's an open problem. Any other question? Any questions? Otherwise, we can move ahead. So we can prove that for the intersection number for, the cover number for the intersection function is also roughly 2 to the power n by 2, roughly. The constants don't matter, like among friends, constants don't matter. So I'm just going to look at the dominant term here. This proof is needs a small observation that the intersection function or the graph corresponding to it can be broken up into two parts, A and B, such that this graph has a partition number 2, and the second remaining part, B, is a tensor product of intersection of size n minus 2 with a graph H, where H has partition number 2. So this proof follows that outline. And yeah, once someone gives you these structures A and B, this argument is very easy to make. So at this point, I want to quickly summarize all the additional research areas that one can consider. So first of all, what if we decide to go beyond flat distributions? We want to consider X and Y joint distributions that are general probability distributions. Then instead of P4-free bipartite graphs, this problem translates into a variant of non-negative matrix factorization problem. This is another interesting question. What if the Genie does not provide the same suggestion Z to both Alice and Bob? What if the Genie provides Z subscript A to Alice and Z subscript B to Bob? So surprisingly, asymmetric suggestions do not help unless you are looking for some special kind of problems. Let me mention a problem where asymmetric suggestions may be useful. Suppose we want to consider the smallest assistance of Genie when Alice wants to obtain 2 bits of randomness and Bob wants to obtain 3 bits of private randomness. Restricted to such problems, asymmetric assistance might be useful, more useful than symmetric assistance. What if the Genie is randomized? Again, this is something interesting, and we do not have a good understanding of this. The short answer for our kind of problems is that randomized Genie don't help. They might be useful for the special type of problems that I mentioned. This problem is somehow feels somehow very natural to me. So instead of exactly partitioning a graph, edges of a graph, or exactly covering the edges of a graph, what if you are allowed to add or delete epsilon fraction of the original graph's edges? This is a significantly robust version of partitioning and covering number. And this is related to stability theorems in extremal graph theory. And interestingly, the constructions that I provided for high partition numbers and cover numbers, those constructions still hold for this problem as well. Okay, and let me also mention one point. You do not need epsilon to be very small to be meaningful. If epsilon is as large as a constant less than 1/6, whatever result you get is useful and meaningful. There are application scenarios where they will be useful. Okay, so you should not think of epsilon as 0.001. You should think of epsilon as 16%. If you can show that the partition and the cover numbers are significantly lower when epsilon is 16%, it is extremely useful result. In our entire discussion, we always use the support of Z, that is H0 of Z, and we were trying to minimize that quantity. What if we use different optimization measures of Genie's efficiency? For example, if you, what if we consider the entropy of Z? So I'm not going to go into further details of explaining why this could be interesting, but I can find applications where minimizing HZ has more meaning, is more relevant to the problem setting. In fact, you can consider even Renier entropy of other different kinds as well. So with that, I want to thank my collaborators, Simina, and my graduate students, Himanshi and Tamalika. And I want to also thank the funding agencies. Without their support, this work would never have been completed, I think. Yeah, if you have any questions, yeah, please.
Thank you, Maji, very much. Any questions or comments?
Maji, I think it's a very nice stuff and very well presented, actually. And I think it's good stuff.
I can send you the slides.
Thank you.
I can send it to Brent and he can put it on the website. I do not have any problems with that.
Okay, good.
Yeah,
Brent can do it.
Yeah, that would be excellent. Thank you. Any other thoughts or comments, questions for Maji?
So regarding the randomized Genie,
yes,
I feel like maybe a relevant thing to look at is the fractional version of the click.
Yes.
The cover and
yes. So this is a very interesting problem. Yes, let me just give a short answer. Yes, you are correct. We have to look at the linear programming version of these graph theoretic problems. And historically, there is evidence that these fractional versions or the linear programming versions have better solutions than the solutions when they're not randomized. For example, if you consider covering with rectangles problem instead of P4-free graphs, the fractional cover problem is at most the deterministic solution. Yeah. So there are results of that form historically. Oh, I should also mention that there is another graph theoretic problem. The edge click. This is not a bipartite graph. It's a graph over n vertices, and you try to cover it using clicks. And I did not include that example in the talk today knowingly, because I wanted our intuition to be very fixed to we should just concentrate on bipartite graphs, not general graphs.
Okay, thanks.
Any other questions, comments? Okay, well, thank you again very much, Maji, for the presentation today. And yes, we will post this, the video, as well as we can get the slides from Maji and spread that a little further. With that, I just want to thank everyone for joining us this afternoon, and everyone stay safe for the holidays. And with that, we'll see you next time.
Thanks for having me.
Thank you.